The DC line, this is the next part, and DC line or load line. This is very important to do for any transistor circuit. And to draw it is very simple. Actually, it is a current IC, the collector current, versus the collector emitter voltage, VCE and IC. So it's similar to the previous one here. As you see here, this is also IC versus VCE. But here, the load line is what? Load line, this is the line that has all the points or the possible points, operating points for the transistor. So, for example, if the point is here, if you calculate IC and VCE, it will be located on this load line. If, for example, if the voltage VCE is here, for example, then you know that the current will be here, and so on. Why? Because the point, as I said, the point is all the operating points are located on this line. And to draw this line is very simple. The idea is very simple. We know that the relation between the current IC and VCE is like this. This is IC. Then if we just need 2 points, if IC is 0, so IC is 0 here, this point here. If IC is 0, this means that this is 0, which means that this is 0. Means what? VCE equal VCC. That's it. So VCE equal VCC. And we call this the cutoff VCE voltage. And if VCE equals 0, here, this point, VCE equal 0. Then in this case, this is 0. Then IC equal what? Equal VCC divided by RC. And we call this IC saturated. This is the maximum collector current, and this is the maximum VCE. You cannot exceed this value or this value. All the operating points must be located on this line. So this is the summary of all what I have mentioned here. Okay, so let's see, for example, this is the example that we have solved before. Okay, so what happened here? This is this is the example that we have solved before, where this is a 10 volt and 200K and so on, 0.7 and so on. So let us see what we have here. Assume that beta equal 100. Beta was 100 before. So let us see the numbers. Let us see here. Select all, then delete. So in this case, if you want to decide what is the how the load line look like, doesn't look like line at all, but okay, here it is. Okay, so this one here is VCC. VCC is 15 volt. So here is 15 volt. And this one is what IC is VCC divided by RC. VCC is 15 divided by 1, so it is 15 milli. 15 milliampere. Let me increase this a little bit. Yeah, this would be better. So now, the operating point is located on this line. So where it is? Where is IC? Where is VCE? If this is a point Q. So you can start calculating any one you like. But of course, here, how you calculate it? First, you calculate IB. And then after that, you calculate IC. Then you calculate VCE. This is how you do it. This is a sequence here, VCE. Then IB equal what? Equal 10 volt minus 0.7 divided by 200K. So here, let us calculate it. Let's get a calculator. 10 volt minus 0.7 you divided by 200K. So this is 0.046. 0.0465. And since you are dividing over K, then it will be milliampere. This is the current, the base current. if you want to calculate IC, IC is beta. Beta is 100. If it is 100, so it's just multiply this by 100. So this will be the current. Here it is. That is 4.65. 4.65 milliampere. Then you calculate the voltage VCE, this voltage here, the voltage VCE, this voltage. It is what? It is 15 minus the voltage across this resistor RC. So it is 15, so it's 15 volt, minus the current, which is 4.65, times the resistance, which is 1. Of course, kilo will cancel with milli, then it is equal to 10.35. 10.35. So this one will be around 10.35. And the IC equal 4.65 milliampere. And this one is, this is 3, supposed to be 3. Okay, and this is volt for sure. So these numbers are right. Why? Because they are within the range. This one is 0 to 15. Okay, so 10.35 is fine. Same for the current. So this is the operating point now. What if I change beta to 200 instead of 100? Make it 200. What will happen? Of course, IP is the same. So IP is 0.0465. IP is the same, but you multiply it by beta 200 to get the current IC. So IC is 9.3. So now this will be 9.3. Somewhere will be here somewhere. Will be 9.3. Oh. Make it different color. Come on. It is. So here it is 9.3 ampere, milliampere. So this will be the second point, Q2. If we assume that this Q1 when beta equal 100, Q2 will be when it is 200. Beta is 200. So now, according to this, VCE will be here, will be this location here. Then it is less than 9.35. So let's calculate it. This is the current. The current multiplied by 1K. This is the voltage. So 9.3. Okay. Voltage 9.3 times 1 is voltage. Is the voltage across RC. Minus, make it minus, and then add 15 volt. So it will be 15 minus the voltage. It's 5.7. So now this is the voltage across or between C and E, 5.7 volt. Okay, this example here show us what? Let's see the result. We will get the same result as we have here, I'm sure. So this point and this point are the same. This point and this point, oh yeah, they are right here, 9.3 and 5.7, and 10.35 and 4.65. You can notice what here? You can notice that when you change beta, the location, the operating point is changing a lot. There's a big difference. You see, the voltage here is 10, the voltage here is 5.7. You see, it's almost double. And here the current 4.65, the current here is 9.3. Let's see, double. So this is a problem in this biasing system. When you have, this is a ground, and you have what we call base bias. When we have a voltage here and a voltage here, and we have a ground here. So this is a problem, that it is unstable. Why? Because beta is subject to change. Beta is a function of the temperature. And as I said, when you have a current, the current will heat the transistor, and when it heats the transistor, beta is increasing. And you see here, beta is 100, become 200, for example. And when beta increase, IC increase, because IC, the current IC is beta times IP. So in this case, the current increase. When the current increase, there will be more heat, produce more heat. Then when you produce more heat, then you have more Q, and so on, more beta, and so on. So in this case, you can damage your transistor. Let us see another example, or this was the last example in this chapter. Let us just solve some problems here, some simple problems. Find beta if alpha equal 0.99. So we know the relation here. We just use the relation. Beta equal alpha divided by alpha 1 minus alpha. So it is 0.99 divided by 1 minus 0.99. That is 99. If beta is 200, what's alpha? You use the relation for alpha. Alpha equal beta over beta plus 1. So it's 200 over 200 plus 1. That's 0.995. This is a common base or common emitter transistor. Then if we want to calculate, this is similar to the ones that we solved before, but different numbers. So we need to find all the currents, for example, in this circuit. First, if you want to calculate or make the load line. So to make the load line, first you need to know what's this point and what is this point. According to this, we know the relation between VCE and IC and VCE, which is this one here. This one is the same like the previous one, but just look different. So this one is the same like this relation. There's no difference. Okay? So here you can multiply RC times IC, and then you move it to the other side. Then VCE equal what? Equal VCC minus IC times RC. The same relation. So from this relation, you can draw the load line. So when IC equals 0, VCE equal VCC. Here it is. It's 20 volt. So 20 volt. And when VCE equals 0, this VCE equals 0, then IC equal VCC over RC. So VCC is 20 divided by RC, which is 2K. Then it is 20 divided by 2K, that is 10 milliampere. So we know that all the operating points will be located on this line. Of course, if you have different Q. Okay, so let us now see what's beta, the different beta, sorry. Beta is 100 here. Beta is 100. So the steps as regular. First, we calculate the current, IP. So IP is this voltage minus this voltage, which is 0.7. 5 minus 0.7, that's 4.3, divided by 200K. 200K, the resistance. This will give you the current IB. And the IB, you multiply it by beta to calculate IC current, this current. So this current will be 100 times this number here. So it is 2.15 milliampere. And if you want to calculate the current here in the emitter, the current in the emitter is the summation, IB plus IC. This is the current in the emitter. If I want to calculate VCE, the voltage here, so this voltage equal what? Equal VCC, which is 20 volt, minus the voltage across this resistor, which is IC times 2K. IC times 2K. Okay, so VCE equal VCC, which is 20 volt, minus IC. IC is here, and RC is 2K. So this will give me this voltage here, 15.7. If you want to locate this on the graph here, so the 2.15 is here, and for 15.7 is here. So if you wanna, if you draw this one exactly to scale, and if you locate 2.15 and then draw another line here, you will find that the value is 15.7. Must be. Okay. So this one beta equal 100. If you change beta, you will change these numbers, as I said before, because this system, this one here is unstable. Is not constant here. Is a function of beta. Beta, when beta change, the operating point will change. Let us see a different problem here. We have this light emitting diode or LED. This LED has a 2.1 volt. Okay. So we have a voltage VCC here. This is certain voltage 5 volt, and we have this RC, and then we have LED, and then we have a transistor, and we have this RB, and we have a voltage here is 5 volt. This voltage is 5 volt. And we want to do the same here. We need to do what? We need to find the current in this LED, this current here. Then this current is IC. This current is IC. Okay, so how can we find IC? To find IC, you need to find IB first. IB equal what? IB equal 5 minus 0.7 divided by the resistance, which is 3.6K. So this is IB. Okay, you multiply by 100 to get IC. So this is the current in the LED. This is the current here. It is that simple. Okay. So now this is the current. But when you draw, as I said, usually you need to draw the load line. Let us draw the load line. So according to this, the current equal what? The current equal this current, the relation here, or VCE equal what? Let's write it. Let's write this. VCE equal what? VCE is the volt shear, positive, negative. Equal 5 volt minus this current IC, so 5 volt minus IC time RC. Okay, but you have another voltage across the LED, which is 2.1 volt. Then you have to subtract those, minus 2.1 volt. Then actually VCE is 5 minus 2.1, which is 2.9. So it's 2.9 minus ICRC. Okay, so this is the relation between the VCE and IC. So now if VCE equals 0, if this VCE equals 0, then IC equal 2.9 divided by RC. IC equal 2.9 divided by RC. RC is 270. So let's calculate this. So IC equal 2.9, 2.9 divided by RC, which is 270 ohm. That is 0.010, for example, 0.0107. So this is the number here. Okay, this number is this number, but you can, if you multiply, if you want to do this, this is in ampere, so it is equal 10.7 milliampere, 10.74 milliampere. Okay, so now this is this point here, 10.74 milliampere. What about this point? This point here, when IC equals 0, if IC equals 0, VCE equal 2.9 volt. So this is the load line. Then now any operating point should be located on this line. But what happened here? That IC, when it is calculated here, it is not one. It is 119 volt, 19 milliampere, much larger than this number. Then this will not work. Okay, this is the maximum current. The maximum current is 10.74. Cannot exceed this number. So the current will be this number. Because that's why it is important to plot the load line. Because sometimes when you calculate a number that exceed the limit. Okay, and you cannot increase the current more than this number here, 10.74. It's the maximum. You cannot get more than this number. Okay.